Hello and welcome back to this part 2 video of a two-part series. We're talking about microcontrollers and microprocessors. In particular, this particular video is going to be looking at the Arduino development board with its ATMega328p microcontroller on it. We're going to be looking at this board here connected to a couple of LEDs and a switch, and we're going to be looking at different ways to what we call debounce, or if you like, clean, filter out the signals coming from the switch to drive an interrupt pin on the Arduino. There are different ways to do this. You can do it with a hardware solution, okay, actual components on the protoboard, and you can do it with a software solution where you don't use any components externally for filtering or anything. You do it all in the software. So two different methods, and we're going to be looking at both in this video. Here we go, and let's start off looking at the hardware solution version first, and later in the video we'll be looking at the software solution. Okay, so here we are in the IDE, and we're looking at the software that we're going to be using for the hardware button circuit that we've set up here. So every time we're going to press the button, what we're going to do is set off an interrupt, and I'll show you what we're doing in the code here. Now, because we're using a hardware solution here, all of the contact debounce that we're going to be talking about soon, that's going to be taken care of in hardware. All this software is going to do is take a clean interrupt pin, if you like, a low to high and a high to low logic level, and we're going to basically flip the state of the interrupt status LED and change the flash time of the other LED. So there's two things going on with the LEDs there. So let's have a quick look at the code. I'm not going to spend too much time going through this line by line like we did in part 1 of the video. I'm going to assume that you've kind of got the idea of things like comments and that sort of thing, so I'm not going to talk about stuff like that anymore. So these are all constants at the top here, and what we've done is we've added a button, and we've called that button pin, which is again is a constant of type int. We already had LED pin flash, that's the same, and that's connected to pin 13 on the Arduino board. And we've added this other LED called LED pin int, and this is going to be our status LED for fast and slow speeds. So when we actually press the button, it's going to flick between fast flash speed and a slow flash speed. And this LED is connected to pin 12. So just like before in part 1 when we saw the LED connected to pin 13, now we've got another LED connected to pin 12 as well, and that's the button on pin 2. It's actually not directly connected to the button, it's through the hardware circuit we'll be looking at very soon. Okay, now we have this LED state, and this is going to be a variable. This is RAM, remember. This is going to be a variable for whether the LED is in a fast state or in a slow state mode. Under that we've got our sleep time variable. Now what's all this about? So if you remember, we used to have a delay in main, it had a fixed value of 1000 in it. Now we've took that away for the actual flash speed, and instead of it being hard coded as 1000, we've now made it a variable called sleep time. Here we're assigning the value of 1000 milliseconds, if you like, 1 second, into the variable sleep time, which we use in the main code in a moment. Now we've made it of type int, type integer. We know what that means now. It's just a number, whole numbers only, and we've got this keyword here, volatile, in front of it. So what's that for? I'll quickly mention what that means. Basically, volatile is if you have a variable that could be changed outside of the code that you're already doing. It means sometimes when you do a compilation, the compiler has optimization. In other words, it reduces anything that it thinks it doesn't need. If it sees variables that are not being used, things like that, it will just not bother putting them into the final code, and that's to conserve memory space when it goes to the target device. So whenever you've got code in a function, in one function, and it thinks, that's not actually being used for anything, it'll just remove it if your optimization setting is set quite high. What volatile does, it says, right, ignore the fact that you think it's not being used, because it is being used elsewhere in another function. Alright, so if it's being accessed or changed from another function, and we get this sort of problem when we start using interrupts, the compiler will think, well, that variable's not doing anything, so I'm just going to remove it. But actually it is doing something, because it's been changed from a different place, from a different chunk of code. And like we said before, when you jump out of the main code, when you get an ISR signal, it actually runs the ISR, the interrupt service routine code. That variable sleep time is going to be changed within the ISR routine. So the compiler might think, nothing's happening with sleep time, it's not being changed anywhere. Well, actually, yes it is, it's getting changed elsewhere. So we use the volatile keyword to say, don't optimize it, it is getting changed and it is in use. Put it in the code. So if you like, we're one step ahead of what the optimization in the compiler thinks we want to do. We're telling it otherwise, and we're saying no, keep it in. So mode, and this is initially set to false. In our case, mode equals false means slow. We're going to actually say if it's false, then flash the LED slowly. If that was made true, then flash the LED quickly. Right, that's all of the initialization done. Let's have a look at setup. Now, as you know, setup is the first function that we actually come across, where it's an Arduino function. It's not standard C, so it's a little bit higher level, as we mentioned in part 1 of the video series. So I won't go into that again. And all of the code is in this block here. Okay, that's what we're going to do before we do anything else. In setup, if you remember, we had this line already in part 1. This is pin mode. LED pin flash. We're going to set it to an output. That means make the flash LED an output pin. We've also added this new pin mode for LED pin int. This is the new LED that we've added, and we're going to set that to a type output as well. So that's our 2 LEDs ready to do something, connected as outputs. Then we have pin mode, which is the input pin. We've given this a variable name of button pin. It's actually the interrupt pin. We're setting that pin to a type of input, so that's different to the LEDs. Now we're sort of sensing logic levels coming into the chip. Okay, we're not trying to drive LEDs with current going out. We're actually listening, if you like, or monitoring the pin for activity going into the chip. We'll have a brand new function here that we haven't came across yet called attach interrupt. And again, this is a helper function built in within the Arduino compiler libraries. It's actually there to help us assign interrupts. This allows us to do what could be 2 or 3 lines of code in one function step, so it makes life easy for us. Attach interrupt. So what we're doing here is we've got another function within a function here, and this one's called digital pin to interrupt. Again, this is an Arduino built-in function. All this is really doing is making sure we get the right interrupt pin assigned for the button that we actually want to operate with. So we don't have to go too deeply into this. In fact, in our case, you could replace that just with 0 if you wanted to, because we're going to actually send it to interrupt 0. Okay, so that just equates to interrupt 0, which is pin 2 of the Arduino board. It makes it more portable. That's what it's for. You can go between different boards, different Arduinos, you know, and this function will still give you the correct pin. Then we've got this here, pin ISR. This is new. Now, pin ISR is a function that we've created further down the code here, and we've called it pin ISR. What happens is whenever we get an interrupt, an active interrupt on the pin, whenever this becomes active, and it can be a rising edge or a falling edge or just a change in any edge, this function will be called pin ISR, which is our code that we're going to break out from main and run this code, pin ISR, and then we're going to go back to main when we're finished at the end of it all. Right? This is our ISR function code. Name, if you like. This last parameter on the end of this function is called rising, and all we're doing is we're telling the compiler to make sure that the interrupt pin is set to detect a rising edge. That means going from a low to a high logic level. If the level goes the other way and it goes from a high level to a low level, it will not be triggered. Okay, so it's only for a low to a high transition. A high to a low won't do anything, it'll be ignored. We could actually set this to falling instead of rising. If you set it to falling, then it's the other way. Then it will detect changes from a high to a low state, and it'll ignore the low to the high state. But we're using rising, so we're looking for a low logic level to a high logic level. The main loop is exactly the same as what we had in part 1 video with a simple LED flasher. It's just the same. We're turning the LED on, we're turning the LED off. Simple as that. And then we're keeping track of the state here, and then we're inverting the state to make it toggle, to make it go on, off. Every time the loop goes round, we're going to change its state and make it flash. The only subtle difference here, and I mentioned it earlier, is this variable sleep time in the delay function. So instead of having 1000, if you like, hard coded in there like we did last time, this variable, if you remember, it's a volatile int that we've set it up as, is going to be initialized to 1000. We've initialized sleep time to 1000, and we'll now put that value into here. So first time the code comes around, that's going to be set to 1000. It's going to give us 1 second flashes initially when we first start the program without doing anything. But it means we can change this. That's the point here. We can change the speed of the flash time. It's not just going to be fixed with as 1000 anymore. Gives us more flexibility. We can alter it. Now this last piece of code here is the, if you like, the interesting bit for this part 2 video, and this is the interrupt pin ISR function that we're going to be calling from the assignment, from the attach interrupt. It's calling this code here. Everything in these brackets here is going to be executed, and don't forget this is an interrupt piece of code now. This is what we call an interrupt service routine, and this will be called, and we will jump out of the main code. We'll jump out of it no matter where we are in the code. We could be at the top line here, we could be down here turning the LED off, we could be in the middle of updating the toggle, we could be in the middle of a delay, even right in the middle of an actual delay sequence where the process is not supposed to be doing anything, just waiting. Doesn't matter where we are, when we get this ISR triggered, it will jump out of that code and will run everything here. And I've got a little comment here, just copy the interrupt button state to the int LED in brackets mode, because it's either going to be fast or slow, and change the flash speed at the same time. What we're doing here is check our initial state of mode, and if mode is equal to false, then we're going to turn the int LED, status LED if you like, we're going to turn it on. So if we were in a slow mode, in other words false, we're now going to put it into a fast mode and turn the LED on, and we're going to change the sleep time. And as I've already mentioned, sleep time is a volatile int, and we're going to update the value of that right here in the interrupt code, not in main anymore. I'm going to do it here, and that's going to change the actual delay time. There it is there. It's going to alter that value there, sleep time. So now we're going to make it 100. That's 100 milliseconds. So it's going to be LED on for 100, LED off for 100 cycles. So it's going to flash pretty quick, like a fast flashing action. If we were already in a fast mode, then this wouldn't be true, and we would do the else. If you remember, else is like or else. If that didn't work, then do this instead, and we do this. So then we're going to turn off the int LED, the status LED will then go off, and then we're going to set the sleep time now to 1000 milliseconds. So again, we've updated sleep time there to 100 for fast and 1000 for slow. These values get used in the main code, and that is actually going to alter the delay time of the flashing rate in the main code. When we eventually come out of the ISR, remember, we'll go straight back to what we were doing before. That would have been updated, and that's why that value has to be a volatile. So the compiler knows to leave it alone and don't remove it because it's not doing anything. If you didn't have the volatile, the compiler would probably say, okay, you've set sleep time to 1000 if it didn't have the volatile on here, and in the optimization process it could have just put in manually 1000 in there, thinking, well, it's never going to be changed, and it would have actually just made the whole statement delay of 1000. Problem is, of course, we do change it here and the compiler doesn't know that, so that's why it has to be volatile. And at the very end of the ISR, we update the mode variable, and we basically toggle the mode. So every time you press the button, every time we go through the ISR code, the mode will be fast, slow, and so on. Every time you press the button, every time we get a transition on the an edge detected at the interrupt input. And that is the code. Let's go and have a look at the hardware involved to actually activate this interrupt, to connect the button to the interrupt pin, so this code works effectively. So here we are with some information about the hardware solution, the hardware way of actually removing contact bounce from the switch. And there's a few things to explain here, so I'll just go through it one at a time. But first of all, let's just talk about the actual schematic diagram for the hardware solution. So I'll just explain what we're looking at here, and you can see we've got the little push button here. Okay, that's our push button, which is basically going down to ground, down to 0 volts, and we've got a 220 ohm resistor in line with that. I'll explain what that's for in a second. We've got a 2.2 microfarad capacitor, which then goes down to ground, and this is going to be a part of our RC filter circuit. We've got a 10k pull-up resistor which goes up to plus 5 volt rail, and all this is joined together. This then comes through what we call a Schmitt trigger, and in this particular case I found an old one in my junk box. It's actually a 7413 that I'm using, but for the purposes of the diagram, let's just say you can use a 7414. Does the same job, it's just the pin wiring slightly different. Okay, so it's still a Schmitt trigger. The output of that, as you can see, it's got a little circle on the end. We know what that means. That's inverted. So it's actually a Schmitt inverter. You put a 1 in, you get a 0 out. You put a 0 in, you get a 1 out. That drives pin 2, which is our interrupt pin on the Arduino development board. That's going to be driving the actual interrupt either high or driving it low. So what's actually happening here? Well, first of all, let's consider what the signal would look like just at the switch, basically, without the capacitor and without the rest of the circuitry. If it was just a switch going from high to low, Okay, if we didn't have this filter, let's talk about that in a second. Then what would it look like? What sort of a signal would be put into pin 2 if this just went straight through? So no filter, just a pull-up resistor. It would be high state here because of the pull-up resistor, but when you push the button it would then take it down to ground, so that would give us a low state. And you might think, well, why do we need all of this stuff? Why can't we just do that? And every time you push the button we'll get an edge trigger on the interrupt pin and it'll run the ISR code. Well, it's because of this. And if you look at the green area that I've drawn here without cap, this is what it looks like. So you're in a high state, ignore the orange for now, just look at the green. When you're in a high state, when you press the button, this is what it would look like. It would fall to a low state with noise. You actually get a brief moment within about a millisecond or 2 milliseconds, something like that, a little bit of noise when you actually push the button. It's not a clean 1 to 0 transition. And this noise is what we refer to as contact bounce, because basically what you've got inside of the switch itself, we're talking mechanically here, there are 2 metal strips. And basically when you connect that switch on, when you push the button, those metal contacts, if you like, sort of rub against each other a little bit and do have a sort of an action of bouncing, which is why we call it contact bounce, because you get a very brief, it happens very quickly, but it's there, you can see it on a scope. You get a brief amount of like on-off signals. Those on-off signals, the contact bounce that we get from the switch, are enough to trigger the input of an interrupt pin and cause problems. Because instead of 1 pulse, now we're getting 2, 3, 4, 5 pulses, whatever it happens to be. The same happens when we release the button. We get even worse. We get like a lot of contact bounce at the very end before it eventually settles and the contacts settle at a high state. So this is a contact bounce area here, quite bad, and this is another contact bounce which tends to be a little bit faster because you're actually putting the buttons together. There's less of an opportunity for anything to sort of bounce, but at least in my experience that seems to be a little bit worse than that side, than the falling. When you make a connection it seems to be a little bit better than releasing for some reason, although you still do get it at both make and release of the button. That's without the capacitor. We've got this major problem with contact bounce and we need to get rid of that. This is the whole task of this. Back to this filter circuit that we have here. Ignore the Schmitt trigger just for now. Let's just look at this filter circuit that we have to take away the contact bounce. And what you basically have are 2 components. You have the 10k pull-up resistor and you have the 2.2 microfarad capacitor down to ground. And this forms a CR circuit with a time constant, and the symbol for time constant is, it looks like a Greek R there. So this is our time constant. We can calculate what the components have to be, or what the time will be from the components that we select in order to make this fit. And what we tend to aim for here is a filter here which will take out about 20 milliseconds worth of noise. You know, in practical terms, if you look on a scope, anything between 10 and 20 milliseconds is usually good enough to take out, smooth out those rapid on and off transitions. And it also works at the beginning as well. If we aim for something at about, let's say, 20 milliseconds of time, roughly, it's not an exact thing, and it really depends on the condition of your switch as well. Older switches tend to be much worse. You might need more filtering than that. But brand new switches, straight out the box, there's a chance that might be down to just microseconds. It could be less than 1 millisecond. So it's quite a lot of variation depending on the quality and the age of the switch. Bear that in mind. Right, so the time constant we can calculate from here, which is just C times R. So we've got C of 2.2 microfarad and R of 10 kiloohms. And if you work that out, you just get 22 milliseconds, which is fine. You can tell I've already done this beforehand. So the components that we've put in, basically the 10k and the 2.2 microfarad, are giving us a 22 millisecond time constant. Let's move down to this little graph that I've done at the bottom here. What you can see is these figures here. You'll notice that I've got 63% written here and 36% written down here. These are the actual time constant results that you get. The time constant doesn't give you the time it takes to go from, let's say, a complete high 5 volt state down to a low 0 volt state. The time constant gives us the figures between that. It says, okay, how long does it take to get from a full high state down to 36%? Okay, it's not down to 0 anymore, it's just 36% of it. So how long does it take to get from a high down to 36%? That's the time constant. And the other way, when you release, well, how long does it take to get from a full 0 like a constant 0 low level, right up to 63%. We're not waiting to get all the way up to +5 anymore, okay? That would be longer. That's not what this is giving us. It's giving us 63%. That's the time constant. And what you actually end up with because of these component values, you end with something like 22 milliseconds on the release edge. That's called the edge. That's the falling edge, and that's the rising edge. You get about 22 milliseconds there. And on the falling edge, we'll get something like about, I think it's about 2 milliseconds or less than that actually. Probably 1.5, something like that. So that actually smoothed out the leading edge and the falling edge noise. That's going to be perfect. You'll see these green dotted areas here, and these are the actual areas of, if you like, time where the signal is rising and the signal is falling. Within these areas are our actual time constant calculations here. So you'll notice this green area doesn't go all the way down to 0, and this green area here doesn't include from 63% up to +500%, if you like. Doesn't include those areas. So it's just those green areas there are the actual time of interest for the time constant. These are the areas here that we want to filter out. So there's our two components. So what's this 220 ohm resistor here for? There's a reason why we have this. It's got nothing to do with the time constant really, although it does help us with the time constant of the falling edge. That becomes actually the resistance value when you close the button. That's why it's faster here than it is here. It's because of these values here. When you close the button, we're going to discharge the capacitor almost down to a complete 0 level. Not quite a complete 0 level, because you do have a potential divider here. It's not 0 ohms, it's 22 ohms. So you're going to be like, I don't know, half a volt or less than that, 0.3 of a volt above 0. It's not actually going to go down to 0. So what's this for? Why do we even want that? Like I say, it does give us a little bit of RC time constant on the falling edge, which is good. That helps with reduce the noise. But more importantly, it's going to stop the button from being destroyed over time, or let's say degraded in its performance, because what's happening here is, without that resistor, you would be discharging the capacitor's energy straight through the switch down to ground. You know, you could have a good few amount of milliamps, possibly, I don't know, maybe it's even 200 or 300 milliamps, who knows, from a fully discharged 5 volt rail capacitor through the button. You know, you've got quite a few milliamps going on there, and because it's a dead short, so the current is very high. So this resistor is twofold. It's given us a little bit of time constant on the discharge time when you press the button. Makes this a little bit more filtered out, and it saves the button from being degraded over time. After a lot of presses, those contacts would effectively be pitted because of the current flowing through them. So that's actually doing two things, and you could experiment with that value. That's the time constant, that's the filter circuit and the button protect, if you like, as well. This is taking out these areas here. Now if you look at the width cap orange cycle here, orange graph, basically that's all I've said. I've just said, okay, high level, then you push the button, then you get a nice capacitor discharge curve within a very short period of time, actually like probably a millisecond, and then down to a low level, okay, or thereabouts anyway, pretty close to low. And then when you release the button, you get a nice big 22 millisecond release time here, going back up to high. A typical capacitor charge curve there. So you'll notice there's no more spikes anymore, and there's no more spikes anymore here either. All that's gone, and that's our time constant. So at this point, we're looking at this orange point here. This is our orange falling, rising edges here. So you might think, well, okay, why can't we just put that straight into the input pin of the Arduino, into the interrupt pin? Well, there's a couple of reasons, and one reason is noise. If you have any noise on the signal, if you put that straight into an interrupt pin, even if it's mains home or processor noise or anything like that, even if it's very small, like 5 millivolts, 10 millivolts worth of noise, as this voltage goes through the detection point, the threshold point, if you like, where the interrupt says, yep, I've detected a change, whether it's falling or rising, let's say it's rising, at that point it would actually activate. But with noise on the signal, it would be slightly up and down as it goes through, and you could get like a few activations of the interrupt pin as the noise bounces up and down as the voltage rises. So in order to take care of that, we use a Schmitt trigger to take out any noise. That's really what it's for, because the Schmitt trigger will only react to inputs which are away from the previous input. What I mean by that is it creates a gap where a high level going to a low is a different voltage point from a low going to a high. If you like, there's a window where you can't have anything. If the voltage is rising, it's got to go right up to a particular point before it will trigger. If the voltage is then coming back the other way and falling, it has to go further down, it has to pass that point. So the two trigger points, the high and the low trigger points, are different, and you have a hysteresis point, as they call it, between the two, where there is a voltage that you basically can't activate by changing it on the input. So you've either got to go higher or you've got to go lower, and what that does is removes any noise on the signal, because the little 5 volt or 10 millivolt noise on the signal that could be here, then if it's on that signal, it basically falls within that no operation gap and gets filtered out. So it really has to go up or go down enough to actually activate the input of the Schmitt trigger. Now the output of the Schmitt trigger is a very fast rising and falling edge. It's something like about 10 to 20 nanoseconds, something like that, rise time and fall time. It's got a very fast rise and fall time, and it's that digital 5 volt signal at logic level, if you like, which then connects to the input pin, to the interrupt pin of the Arduino. That is then completely clean. You have no noise. It's been filtered out, if you like, with an RC circuit for contact bounce. It's also filtered because we're taking out any noise that could be on the signal, and it's giving us a very fast, within nanoseconds, typically 20 or 30, something like that, nanoseconds of rise time, fall time. So it's a very fast reacting output, and that's perfect for driving the interrupt pin. There's also another reason why we need a very fast rise and fall time driving the interrupt pin. And I've recently been doing some experiments which actually appears to be an undocumented thing on the internet. I haven't been able to find any reference about this at all, but there is actually a minimum rise time that you need for the interrupt pin to work on an ATMega328p, and I'm not sure if this is a problem with other ATMega chips in the same range, but it certainly is affecting this one, which is the ATMega328p. And the problem is that if the rise time, and I've been experimenting with this and it's correct, if the rise time is too slow, you get multiple activations on the interrupt pin. That's interesting. You get multiple activations on the interrupt pin, even if it's completely filtered with an RC circuit and your power supplies are all well decoupled and everything. You put a scope probe on there and you cannot see any noise. This is getting away from what we're talking about here, but I wanted to mention this. So there are limitations with the actual rise time of the Arduino chip, and it's undocumented, like I say. I haven't been able to find any reference to this. And if you're interested, it's actually about, it has to be faster than, around my measurements show, 9 microseconds per volt. So it has to be faster rise time, the edge from 0 to 1, a rising edge or a falling edge, depending which mode you've got the triggering in. And if we just had this capacitor coming out here, that's going to be way slower than 9 microseconds per volt. So anyway, I'm not going to go too far into this. It's probably a subject on a forum that needs to be discussed with other people and see what they think. But it could actually be a design fault within the ATMega328p chip and possibly other chips of that series. The rise time must be faster than around about 9 microseconds per volt. If you make it faster than that, like using a 7414, which gives you nanoseconds per volt, it's incredibly quick, then you have no problem whatsoever with this problem. But if it's too slow, you actually get multiple activations of the interrupt pin. And like I say, I've had to spend some time figuring this out because it's not documented, and I didn't understand why when you disconnect the Schmitt trigger, this rise should actually be clean enough to only give you a single interrupt. When it passes past the detect point, it should just activate it, but it wasn't. I was getting something like about 14, 15 activations of the ISR code every time the button was released or pressed. So that's something which is potentially brand new, and we'll see what people think about it. But anyway, the answer is, the solution is, use the 7414 for two reasons. The very fast rise time, like I've just been talking about, for the interrupt to actually work, okay, because of the peculiarity of the chip. And it's also basically just to remove any input noise that there could be by using a Schmitt trigger and having a different high and low detection voltage. Right, that is the hardware solution. So let's go and look at that in practice on the protoboard. Okay, so here we are on the bench, and as you can see, we've got some LEDs flashing and stuff like that. Okay, well, we have the Arduino board over here, and that's connected through the USB lead to the PC, so we can update its firmware. Our compiled code can be sent to that. We'll have some jumper wires, different colours. Here we are to the protoboard. I've got a couple of switches here, two different types of switch, two different manufacturers, and they're both just wired in parallel, so I can basically play with one and then play with the other one, whatever. And but they're both doing exactly the same thing, and they're both just wired together in parallel, like I say. Okay, so they're our test buttons. A couple of LEDs here. The one that's on constant at the moment, that's the interrupt status, if you like, the fast or slow mode indicator. And at the moment we're in fast because the LED is on. Then we have the flash LED, which is at the moment, it'll be in, because it's in flash mode, it is switching on and off in 100 millisecond cycles. 100 milliseconds on, 100 milliseconds off, and so on. Here's our little RC filter circuit here. We've got a 2.2 microfarad capacitor, that red capacitor there, going down to ground across the switch basically. We've got our 10k pull-up here, 10k pull-up there to 5 volts. We've got the 220 ohm resistor, which is in series with the buttons. And we've got a chip down here, and that's our 7413, which could probably be better if it was a 7414. It's just I don't actually have a 7414 to hand, so I've used a 7413 Schmitt multiple input NAND gates and configured it as an inverter. So it's doing exactly the same job as a 7414. It's still a Schmitt trigger, it's all I had. Okay? Right, sometimes that's what you have to do. It's all wired up, it's all operational, and of course now we can have a bit of a play. So here we go. Let's send an interrupt signal, so press the button and you'll see now we've changed state to off. Interrupt means it's slow, that's our slow mode. The LED is now flashing at 1 second intervals, 1 second on, 1 second off. Press it again, that's fast mode, back to slow mode, fast mode, back to slow mode, and so on. And you can actually play with that quite reliably. I'm not getting any false triggers on the interrupt status LED. You know, that's pretty good. It's not actually false triggering at all. Every time I press, it's consistently changing. And I can try the other button here. Let's try that one. Press, press, slow mode, fast mode, slow mode, and so on. So that's 2 different types of button, both doing exactly what they're meant to do. We've got the button, we've got the RC time constant here, we've got the Schmitt trigger giving us a really fast rise time output through this grey lead here, and that's going to the interrupt pin on the Arduino, and it seems to be working really well. Just to demonstrate the problem further, if we didn't have the RC time constant filter in there, I can demonstrate that and show you what happens if you don't have this circuit. So I can remove the 2.2 microfarad capacitor. I've just pulled out one of the legs of it there, so it's now not connected. So this is the circuit. We've still got the Schmitt in here for the fast rise time, but now we're going to have contact bounce not filtered by the capacitor. So we're going to send contact bounce to the chip, and this is what happens. So let's try pressing the button a few times. So we're in an off state at the moment. We need to look at this top LED here. Right, did you see what happened? I pressed the button, it came on, then it went straight back off again. So that's not right. That worked, that worked, that worked, that didn't work. So I pressed it that time and it was in a fast state, then it went to a slow state, then it come back to a fast state again. So that didn't work, and it's just didn't work again there either. So you can see it's not very, there, it's missed it there. It's just not very reliable, and this button's probably, I don't know, it's even worse. It's not working at all. There you go. So I hope that shows the importance of actually having the RC filter in there. It's about 20 milliseconds, and we're using the Schmitt trigger to make sure that the interrupts work correctly as well, because we need that fast edge for the chip to operate. And here I'd like to explain a little bit about what's happening when we call the interrupt. When we receive the correct logic state on the interrupt pin, that's pin 2 if you remember, what actually happens. Okay, so this is our main code here, and in our case we're running a continuous loop in the Arduino code, in the source code. So we're running through our instructions, then when we come out the bottom we start again. So this is our main loop, turning the LED on, turning the LED off. So this is our software code here. Now what happens when the pin receives the correct logic level, that's going to activate the interrupt service routine, the ISR code here. And of course what happens is we're breaking out of, it could be anywhere within the main code, but we're breaking out. So we'll stop what we're doing here, and then we'll start from the very top of the ISR code and run everything within the ISR code. Okay, so that gets executed, everything in there. When this is finished, then we'll drop out the bottom here and go exactly back to where we left off. This could be anywhere, remember. I'm just showing this kind of in the middle for just for the diagram here. But it could be at the very top, it could be at the very bottom, it could be anywhere in the code. It always comes back exactly where it left off. So that's what's happening every time we get an interrupt. We're jumping out of the main, running the ISR code, and then coming straight back to exactly where we left off. Okay, so this is the other way of doing it. If we didn't want to use hardware, let's say we're in a process of designing a piece of equipment, we're told to keep the cost of the components down to an absolute minimum, and we didn't want to put capacitors on boards, and we didn't want to use Schmitt triggers and this kind of thing. Well, is there anything we can do to get the button to work without using the filter circuit and the Schmitt trigger in order to keep costs down? Well, yes there is. So there is a software solution to this. I'll briefly show one of the methods. There's a few methods to do this, but this is the one that I've used myself, and it seems to work reasonably well. Not 100% perfect, but it's better than nothing at all, and it does mean it works without the external components, so costs are down. Quickly running through this again, I'm not going to go over everything that we've done before. The initialization, the definitions are the same. 2 LEDs and a button input for the interrupt pin. These are variables, again with the volatile sleep time that we're going to be altering from the ISR to the main code, and everything else is the same as we had before with the hardware solution. Up here, again, everything's exactly the same. We're setting up the 2 pins as outputs. We've got the button as an input pin, and we've got attach interrupt again for setting up the interrupt service routine that we are calling pin ISR, and we're going to be detecting, as before, a rising edge. Okay, so up to now, nothing's changed. Loop is exactly the same as it was before, and if you remember, we're going to be altering the value of sleep time, the volatile int of sleep time, and that's going to make the LED delay fast or delay slow. This is where the changes start. Again, we've got our ISR code here. This is what's going to be executed every time we get a rising edge on the interrupt pin. So we've got a couple of things going on here. We've got this this type of variable here called a static unsigned long. Now we haven't seen this, so I'll just quickly explain what's going on here. A long is a 4-byte variable in memory, if you like. It's bigger than an int, and what it means is that we can basically store bigger values. It'll hold higher numbers than what an int can hold. Keyword here, unsigned. That basically means that we're not going to be able to deal with negative numbers anymore. We don't want to use negative numbers for this particular application. It gives us double the range of values that we can have. If this was just a long by itself, it would have a certain amount of values, but it would go plus and minus, and you have to cater for all those values. By making it unsigned, it means, you know, we can get rid of all the negative values and everything can be positive. So it doubles the range of the long. We can have bigger numbers, basically. That's what it means. Double the size is what we could have. And what static means is, normally when you're in a function and you have a variable, when you jump out of that function, when you leave the function, okay, and go and do something else, that value can be erased. It's because the program is going what we call out of scope. By going out of scope, these are local variables, if you like. This unsigned long is a local variable. The one underneath it is also a local variable as well, and these would be erased when you left the code. What static means is, do not erase this when you leave the code. Leave it in memory and don't use it for any other purpose. Don't wipe it or anything, or use it for, you know, stamp over it from another part of the program or anything like that. That's what static means. It means leave it alone. It's going to stay here and it's not going to be erased or wiped out. So when we come back into the ISR the second time, this value will still be set, just like we left it the last time when we left the code. So we've got a variable here and we've called it last interrupt time, and we've initialized it to 0. You'll notice I've got some remarks on the ends of these lines here, and I've called them all debounce, and that's because these are the added lines from the code that we had before. This is really the only difference. It's just it's actually 4 lines. There's a one down the bottom there. So there's 4 lines that we've added. That's all we've done, and this gives us the ability to debounce this switch. So yeah, okay, last interrupt time. Then we've got an unsigned long. Again, this is bigger than an int, and it's unsigned, so there's no negative numbers, but this time it's not static, so this is a temporary local variable, and when we leave the code this will be wiped out, but it doesn't matter because we'll refresh it when we come back in the next time. Now millis is a function, and again this is a library function built into the Arduino IDE, and what this does is it reads the amount of milliseconds that the processor has been running from switch on. It keeps a track. There's a little bit of code behind that. The processor has been instructed to do something in the background, and we can call this function. It's quite handy. It's not standard C, remember. There are other things in standard C to get around doing things like this, but this is built in and it makes it very useful and easy for us to do this. So we can measure how long the processor has been running in milliseconds from when the power is applied to the chip and the program starts to run. It's very handy. And just as an interesting bit of information, it actually can handle up to a duration of 49.7 days or something like that anyway. After that amount of time, it wraps around, so it goes back to 0 and starts counting again. So as long as we're working within 49.7 days, everything will be correct, and then when it wraps around, then something else happens. It'll go back to 0. So we'll keep it. All we're doing here is every time we come into this loop, we're taking a snapshot of the time the process has been running. Then we've got a decision to make here. We're asking the question, well, is interrupt time minus the last interrupt time, which we've initialized to 0 at the beginning, if this result here is greater than, if you remember that's the greater than sign, 200. Okay, so if it's actually greater than 200, then what we're going to do is we are going to execute this code within this code, execute the functions within this code. So if that's true, and if we have actually had a state, if you like, which is over 200 milliseconds actually, okay, so it's actually 200 milliseconds there, just so you know what the 200 means. It means that the time has elapsed. It means, if this is true, it means the button press was actually a valid press, and it's not just noise from the debounce. If you remember the debounce glitches, if you like, the on-off, quick on-off transitions, they're all very quick, usually in the terms of microseconds, or up to 10 or 20 milliseconds worth of noise. We're saying wait for 200 milliseconds, plenty of time, push the button and release it again, and this detects for valid presses of the switch. Okay, if it's shorter than 200 milliseconds, in other words, it's just noise like bounce contacts, that sort of contact bounce, or very fast presses, and it's not really a proper actual human press. Anything that's shorter than that, it will ignore this. Okay, it will not be executed, and we won't change our sleep time variables just like we were doing before. The rest of the code in here, by the way, is just the same as the previous hardware version that we did, and we've got the the mode being toggled at the end of it and everything. So all that bit is exactly the same as it was before. Changing the LED state, making it fast. Changing the LED state again, making it slow. So it's 100, 1000, just like before. And at the end of all this, if this had been a true button press and it's allowed, then we say, okay, interrupt the last interrupt time to the current system interrupt time. The last interrupt time, if you remember, is a static. That means that this is going to be updated with the current system time, and it's not going to forget it when it goes out of scope, when we jump here back into the main function. When we come back with another button press or contact bounce, whatever it happens to be, some sort of interrupt activation, if it's a true press, if it was a real one, it was over 200 milliseconds, it's going to be stored. We're going to take a snapshot of the system time for the next time that we come in. Now if you put all that together, you end up with a software solution for debounce. Fast pulses will be ignored and long pulses will be accepted. In other words, it's assumed, yes, it's a genuine key press. And that is the debounce. It's basically 4 lines. Those 4 lines there are the debounce software equivalent of a hardware circuit. There are some limitations with this. Fast button presses will be ignored. There's also a problem where if you hold the button too long, then it'll actually go over 200, and then when you come to release the button, it'll probably think it's a contact bounce situation. So you can't hold the button down too long with your finger and then release it and expect it to work. So your button presses have to be realistic within a certain amount of time, otherwise you start getting problems with like how big does this value have to be. And a little bit of experimentation on the bench here. I messed around for about 10 minutes and just tried different speed button presses and what have you, and I've ended up with 200 milliseconds, and it seems to be reasonable for a realistic button press. And it's basically these 4 lines that are giving us that ability. So let's go and have a look at the hardware. As I say, we've removed the RC components and everything. We'll go and see if this code does indeed work very well. Okay, so here we are back at the proto board again with the hardware basically, and this is to drive the software interrupt solution to debounce the switch. You'll notice straight away I've removed some components. I've removed the capacitor and the resistor RC, well at least the capacitor anyway, and we've removed the 220 ohm for the to protect the switch, and we've also removed the 7414 or 13 in my case Schmitt trigger chip. So there's a bunch of components that we don't need anymore. That's a decoupling capacitor for the power supply, by the way, so you can exclude that. So we've removed 3 components here. Straight away we've saved a little bit of money. If we were in a production environment, I'm sure the accountants would be very happy with that. Let's have a look at this. So what we still do have is the 10k pull-up resistor. We need that to get the logic level to go high when the button's not being pressed. Other than that, we've still got our 2 LEDs. We've got the interrupt LED, status mode if you like, fast and slow, and we've got our flash LED, which is indeed flashing at the moment at 1 second intervals. So we know we're in a slow mode. That LED's off. That's telling us we're in a slow mode. The buttons are wired up exactly the same like I said. So really the only component we've got to the buttons now is the 10k pull-up. Everything else is gone. Alright, so we're doing this in software now. Let's come in and press a button and see if this actually works. So here we go, press a button. So now we're in fast mode and the interrupt status LED has gone on. So that's telling us we're in fast mode and it is actually flashing fast. Let's try it again. That's now slow. Okay, so far looks like it's working. Fast, slow, fast, slow. So the software is doing a debounce. It's doing the work of what the hardware did. Let's keep going. Fast, slow, fast, and slow. Yeah, looks pretty good. I'll try the other button just for completeness. That's fast mode. That's slow mode. Fast mode. Yeah, it's working. Pretty good. You could actually get away with that. I think you could actually put that into a design. You've got positive button activations going on. You know, we haven't got multiple glitches appearing to run the ISR over and over again. It looks like it's doing what it's meant to do. But as I mentioned, it's not perfect. For instance, if you press the button very quickly, let's just see what. That's handling that actually. Didn't expect really. I thought that might not work, but it doesn't seem to be too bad. Now what if we actually hold the button on a long time? Right, now remember we're detecting a rising edge. Right, so that was a rising edge. Let's press the button again. Let's give us another rising edge. That works. Hold it longer. Now so far it's working. Now that didn't work. You see, I pressed it there and it went back off again. Let's try this button. Hold it. There. That didn't work. It's going on as soon as I press the button. You see that? So it's not perfect. But if I do short, well, you know, like normal, let's say not ridiculously long pushes, yeah, it's absolutely fine. So only when you hold it on long, it kind of gets mixed up, you know. So yeah. The other problem is you can't press it very fast, because remember we've got a 200 millisecond check to see whether it's a real press or not. If you press it fast, you'll notice this is flashing much slower than what I'm actually pressing. It's not reacting to my speed at all. There's a limit to how fast you can actually press the button. You can see that. You can see there. It's flashing much slower than what I'm actually pressing. So there really is like an actual limit to how fast you can press the button. Yeah, it's not bad at all, and you could probably get away with it for most projects, but you have to bear in mind it's not a complete solution, and that's why the hardware version is, in my opinion, actually better. You get much more reliable results with the hardware version, and it means you don't actually have to have those extra lines of code in the software. But if you were pushed from a money point of view, or even a space maybe point of view on a PCB, and there was good reasons to remove the hardware, then this is another way of doing it. It's a complete software solution for the contact bounce problem. Okay, so that concludes the video. We've looked at a hardware solution to debounce the switch, to get a reliable single activation every time you press the switch without contact bounce. Done that in hardware using an RC filter and a Schmitt trigger on the output of that. We've looked at how to calculate the values for the amount of time that you want. And we've also looked at a software solution which basically does a very similar job, probably good enough in a lot of applications, and it doesn't require those extra components. There's two solutions here. You can go for a hardware solution or you can go for a software solution, and they both pretty much allow you to debounce the switch and get good reliable presses. That's the end of this video. I hope you've gained something from it. We'll be covering other aspects of microprocessors and microcontrollers and that sort of thing in further videos, but for now we'll leave it there. If you've got any questions, you can pop them in below and I'll try and answer what I can. Thanks very much for watching. Don't forget, if you're new to the channel and you've found this to be useful, it would be fantastic if you could subscribe and like the video. We like that and it helps us get more views as well. So it's all good. Don't forget to subscribe, give it a thumbs up, ring the bell if you want to be notified of further videos. So thanks very much for watching, and here's to the next time.